want to present our work on numerical uncertainty in linear registration. As you might know, the neuroimaging field is under scrutiny for poor reproducibility. One factor contributing to reproducibility crisis is differences in hardware architecture and operating systems and their versions used to process imaging data. Neuroimaging data is sensitive to subtle numerical differences, which can propagate through the pipeline and lead to different results and irreproducibility. Here we want to study numerical uncertainty in linear registration, as it is a critical pre-processing step for many downstream tasks like segmentation, parcellation, nonlinear registration, and we know these steps are in fact sensitive to numerical perturbation. And the objectives here are first quantify numerical uncertainty magnitude to see how much it is important in linear registration, and then compare numerical stability of widely used linear registration tools in different software packages like FSL, SPM, and ANTs, and then explore to see if there is a possibility to use a numerical uncertainty metrics as automated quality control features. To do this, we use Monte Carlo Arithmetic, which is a simulation technique to quantify numerical uncertainty. We created two versions of each registration tool, and a perturbed one and perturbed version. We registered each T1 image once with the unperturbed tool and 10 times with the instrumented one, and to see how this small numerical noise can affect the final result. We measured the variability using the standard deviation of frame-wise displacement. Essentially, frame-wise displacement is a estimate on how the brain image moves to be registered to the template, and we compare this number metric of the movement for all this 10 MCA runs, and see how they're variable and how we frame the uncertainty as a variability in this 10 MCA runs. So what we found was that numerical uncertainty can reach magnitudes comparable to template resolution and in a scanner head motion. So they can sometimes be really significant. On average, the variability between the MCA runs are not that big for a subject. For example, the median standard deviation for FSL and ANTs are not that big, and for SPM is surprisingly small. But you should just keep in mind that it can be significant for some subjects. The standard deviation can be larger than 0.2 millimeter, which is a threshold for removing a frame due to high motion in a scanner motion, and 1 millimeter, even higher than 1 millimeter for some cases, which is concerning. It is because 1 millimeter is a template resolution. And we see that there is an obvious difference in uncertainty of each tool. SPM is the most stable one and the lowest variability across the MC runs, and for the FSL and ANTs, the variability is comparable. And we think that MC drive measures like standard deviation of frame-wise displacement can be used for automatic quality control. For example, if we compare MC runs for a subject that has a failed registration in unperturbed registration to the one that has is not failed, we can see that clearly the variability between MC runs quite higher for the failed one. So just based on the standard deviation of the frame-wise displacement, we can tell that probably the registration is failed or not. You can see it here as a plot. So a standard deviation for the past quality control not failed registration subject is lower than those that failed. For SPM, FSL, and ANTs, all is happening. So there's a hope to use this as a feature for automated quality control. Thank you for your attention to this presentation.